Hello, everyone. It's a big pleasure to be here in this prestigious webinar series on PDEs and applied math. I will present the talk entitled Extremum Seeking through Delays and Partial Differential Equations. And I also like to thank the chair, Juan Climaco, for his kind invitation. Indeed, the topic of research is very important to me, since it is based on the results of my book with Professor Miroslav Krstić. This book was recently published by Science in 2022. Indeed, this is the centennial of the Extremum Seeking invention. And with this book, it's a labor of the last 8 years, we make an ambitious first venture into the vast space of possibilities of designing Extremum Seeking algorithms for infinite dimensional systems. So I hope you enjoy it.
So this story starts when I was a visiting scholar at University of California, San Diego, and this work was started to be developed with Professor Miroslav Krstić, and the main contributions will be presented today came from this collaboration. So this is the outline of the talk. We're going to start with a brief introduction of standard extremum seeking in both versions, gradient and Newton cases. We're going to discuss about static maps and dynamic maps. After that, we're going to start to show the main results, extremum seeking for hyperbolic PDEs, and after that for parabolic PDEs. I'll try to give you some applications of the methods so that you can appreciate it better. And at last, I'll give you some potential extensions to nonlinear partial differential equations and multiple partial differential equations, right? Finally, I'll give you a very recent result using the tools developed here for the non-cooperative gains under delays. And finally, after that, I will conclude the talk. So it's important to mention that extremum seeking is a model-free real-time optimization method, which is oriented for locally quadratic maps. You can try to optimize the map or even its derivatives. You can see in this example that this function theta has a derivative with a maximum given by theta equal to 2, right? So we can try to formulate the problem for the maximization of the derivative, or in the classical case for the function, if this function has an extremum. In this situation, we can formulate this assumption that we need to, the map which we want to maximize has an extremum. This extremum can be a maximum or a minimum. So the extremum point will return this first relation. And the second condition that we need to guarantee is that the derivative n plus 2 of the map must be negative for the maximization problem or positive for the minimization problem. In general, in the neighborhood of the maximizer or minimizer, we can approximate the map for this quadratic relation. In this talk, we're going to consider the case of maximizing the all map. And in this case, n is equal to 0, and our maps will be restricted to the one input and one output. So let's discuss a little bit more about the difference between the gradient and Newton methods. This is the basic block diagram of the gradient extremum seeking. You can identify here an integrator and some perturbation signals, the additive jitter ST, the multiplicative jitter MT. So these signals are chosen as sinusoidal functions, and we need to set the amplitude and the frequency of these signals. Of course, you have an adaptation gain, Q, and the basic idea of this block diagram is try to estimate at this point an estimate for the gradient of the map Q. So the adaptation will try to update the estimate theta hat in order to approximate theta star. In this sense, we can define the estimation error theta tilde like that. And if we compute the aerodynamics, we can write this expression. It's difficult to analyze this expression in the real variable, so we're going to appeal to the average aerodynamics. We need to recap the average theorem. So if you have a system which has an average system computed in this way, the average theorem says that there will be, if the average system is exponentially stable, there will be an exponentially periodic solution represented by z bar, which is bounded by a small parameter if omega is chosen sufficiently large, and ZT, the original system, will approximate the periodic solution as time goes to infinity. In this sense, we can write this average aerodynamics, where K bar is K H, K is the adaptation gain, and H is the Hessian, defined here. Okay, the second derivative of this map with respect to theta. And finally, we can conclude this expression. If we decrease the amplitude of the frequency and the amplitude of the perturbation signal, and if we increase the frequency, we can obtain a small residual set. The Newton-based extremum seeking, the main difference is that we include a cut filter. The idea is to obtain estimate of the inverse of the Hessian, so that when we multiply gamma by G, we can kill the dependence of the algorithm, the convergence rate of the algorithm with respect to the Hessian, right? In this sense, we can obtain a user assignable algorithm where K bar depends only on the adaptation gain, right? Okay, so moving forward to the dynamic map, this is the new system that we want to control. We need to assume that the dynamic part has an equilibrium which is locally exponentially stable. X equal to L that theta is locally exponentially stable, in the sense that we can derive a static map in the static state composed by H, this is the output function, and the function L. And of course, again, this function needs to satisfy the previous assumption given in the very beginning, the beginning of the presentation. So there is a rigorous way to analyze this kind of systems using averaging and singular perturbation. We don't have time to mention all the details, but I will try to give you the main points. So the theorem that we can obtain is that the output of the system converges to a neighborhood of this maximum, and the neighborhood is of this order. Different from the step map case, in the dynamic map, we need to set omega sufficiently small to decrease the residual error. So now going to our main contributions, we're going to expand the extremum seeking to hyperbolic PDEs. The simplest example that we have for hyperbolic transport, hyperbolic PDEs is the transport PDE. These developments were given in our tech paper in 2017. And in this paper, we discussed both gradient and Newton versions for constant delays. We dealt with maps with input and output delays, and scalar maps, and the general setup where we consider multiple inputs with distinct input delays. So let's study the simplest case, considering only scalar maps with output delays. Of course, this delay can be moved to the input. So it is clear that we can consider the same approach for the case where we have actuator delays. Basically, what we need to do when we include the delay is that we need to add this block. Basically, this block is a predictor for the gradient, and I will explain why we need it. And we need to delay these two multiplicative signals, right? Okay. These guys are the same of that we were considering before, but they have a time shift of d. We can see the equations here. And this is the closed loop equation. When we don't use the predictor here, it's clear that the average system has a delay. And if this delay is arbitrary, the system goes unstable. So there is a need to compensate this delay. If you compute the expression for the derivative of the Hessian estimate, we obtain this expression. We can obtain an estimate for a future estimate for the gradient from this expression. This future state is given in this expression. Basically, we are using the variation of constant formula, considering the initial time t and the final time t plus d. It is implementable because we are using just the estimate in the current time, and we are using the past values of the input. So by technical reasons, we need to add this filter to apply the averaging theorem for functional differential equations. And there is a practical advantage of using this filter which is to guarantee the inverse optimality. It means that we can improve the performance of the closed loop system using this filter with C sufficient large. Another way to generate alternative jitters is to not delay the multiplicative ones, but just advance the additive jitter. It's missing here. Sorry for that. Basically, if we move this delay to this point in the input of the integrator, we need to compensate the delay in this signal, and the easiest way is just to apply a time shift in the additive jitter. Right? And this is called trajectory generation problem in a general setup of partial differential equations. So we need to take two measures. Compensate the effects of the delays in the additive jitters or in the multiplicative jitters, and to apply a predictor. So this is the main theorem. So if we choose C sufficient large and omega sufficient large, the state defined by theta tilde t minus d and u sigma in this time window, yes, the control is a part of the state due to the inclusion of the filter C over S plus C, the lag filter. And we can obtain we can guarantee the existence of an exponentially stable periodic solution, which is bounded by this expression. And finally, using the averaging theorem by Haley and Luna for infinite dimensional systems, we can conclude that the parameter theta goes to a neighborhood of theta star. The neighborhood can be controlled by decreasing A and increasing omega. In a similar way, we can compute an upper bound for this difference, which means that the output is going to a neighborhood of the extremum y star. I didn't know if you have followed that, but when we theta approaches theta star, this term is eliminated and the extremum is exactly y star as desired. So sorry for going back. The proof is, we don't have to give the complete proof, but I'll try to clarify why this is an infinite dimensional system. We can write the aerodynamics like that, okay? And if we define the delay there such this expression, we can simply using the PDE formulation, which was provided by Professor Christich in his green book, we can rewrite this equation using the PDE formulation. If we compute the derivatives, we can obtain this setup, and we have now a cascade of a PDE with an integrator. It's very easy to see that if x is equal to 0, we have the delayed signal ut minus d, which is the input of the integrator as desired, right? Okay, well, the derivative of the bar theta is theta tilde. Theta tilde is ut, theta tilde t minus d is ut minus d. Okay, and after that, we need to use the backstepping transformation, and in the new target system, we can use the Lyapunov-Krasovsky functional and prove that target system is exponentially stable. And after that, using the inverse of the backstepping transformation, we can prove the same properties for the original system. And finally, we apply the averaging in infinite dimensions to conclude the results of the theorem. I have some simulations here. We can see that without delays, the system works very well. If we include the delay but no prediction, the system goes unstable. And after including the predictor, we fixed it, right? So we have here some important variables. I call your attention to the estimate of the Haitian, because we don't know the Haitian H, but we can construct an average-based estimate using the periodic perturbations. So an application, a possible application for this theory is in neuromuscular electrical stimulation. Of course, this problem is very hard to solve. We have different problems here. Basically, we cannot construct a good model for the system, and this is interesting for Extremum Seeking because Extremum Seeking is a non-model based approach, and especially we have time delays in this neuromuscular models, right? So in this sense, we want to provide a closed loop feedback strategy which can help the stroke patients in their rehabilitation. This is the scheme that we have constructed. This is the neuromuscular electrical stimulation. We have some electrodes in the biceps and triceps, and this is the apparatus here that we have constructed to our tests. This is the measure variable, the output, right? And we're gonna use this in our feedback. Basically, we are measuring that angle. We compare this angle with the reference. We generate an error. The extremum seeking controller will compute the gains of a PID control in order to minimize this functional and generate the correct electrical stimulation to be employed in the biceps and triceps. What we're trying to do is to perform repetitive movements. If we stimulate the biceps, we can promote flexion, and if you stimulate the triceps, you can promote extension. Composing these two stimulus, you can obtain the complete movement, right? But we are doing this without knowing a good model for the system. So here we can check some results with a stroke patient. In the beginning, we want to follow the red curve, right? This is the first cycle, the second cycle, and so on. We can see that in the very beginning, we don't have a good tune for the PID. The system is not, the closed loop system is not responding very well. But after some cycles, the gains are being adapted in order to minimize the cost function. We finally obtain good result. Here we can see that the control in the actuating in the biceps and in the red curve in degree 1 when we actuate the triceps. We're gonna show some more applications at the end of the presentation involving traffic control and non-comparative gains. I think it's better to discuss this at the end so that we can collect all the information and then figure out the complete scenario. So in this part of the presentation, I will show external seeking for another class of another type of hyperbolic PDEs of second order, and it gives us the wave process or wave equation. It is very important in mechanical and light waves or acoustics and electromagnetics and fluid dynamics. The results of this part of the work were published in this journal, recently published in 2021. And what we are doing now is replacing the delay block by this wave process. The objective is the same. We want to maximize the output, okay? Although we consider, we assume that the coefficient or the domain of the wave process is known, the map is totally unknown. We don't know theta star and y star. We can call this approach like a semi-model based approach, right? So in this sense, we change the transport equation by this wave equation, and we need to redo the design of the signals, the additive signal, and of course, now we cannot use a predictor, but we need to use a wave PDE compensator, okay? I call your attention to this Newman interconnection. In the previous approach, we were using the Dirichlet condition. We were actuating directly in the boundary alpha dt, and here we are actuating in the special derivative of this boundary, right? In this sense, we need, as I said before, we need to redesign the jitter signals. In this sense, what we need to do is, in order to guarantee a sinusoidal function here, as in the classical external seeking, we need to add a signal here that passing by through the wave PDE, we obtain the sinusoidal function. So this trajectory generation problem results in this solution that we show in red. Okay, we define some estimation errors. The estimate error is given by theta tilde, and this var theta gives us the propagated estimate error. It's like the estimate error propagating through the PDE, wave PDE. These are the equations. Note that now we have a second order hyperbolic PDE, and if we check this reference in Journal of the Franklin Institute, we can find the appropriate boundary control for the wave process. Of course, you need to pay attention that we are not using the parameters that we don't have of the map, and we need to obtain average-based estimates for that using these perturbation signals, right? I call your attention. You use n multiplied by the output to obtain an estimate for the Haitian, which appears here. Okay, this is the signal that we are using. This is the same signal which is used in Newton case in the very beginning of the presentation. Of course, this is a much more sophisticated PDE boundary control. But once you have the appropriate backstacking transformation, you can obtain it. So I call your attention to this reference. Finally, we can obtain a similar theorem. The main difference is that now we are involving these other terms of the infinite dimensional state of the PDE, because it's a second order PDE, and we need to compute the periodic solution for these terms. Again, this norm is bounded by a residual set of order 1 over omega. It means that with increasing omega, the periodic solution will be small, and since the real system converges to the periodic solution, the real system is converging to this residual set. We can use the same arguments to obtain these other bounds. In particular, I call your attention to this one. It is related with the amplitude of the additive jitter ST, which was modified in the trajectory generation problem. So we have some plots of the PDE states. Indeed, we are seeing that the parameter theta, capital theta, is converging to the theta star. As well, the other boundary is converging to theta, capital theta star and theta star. Indeed, in the wave process, theta star and capital theta star are the same. They have the same steady states, right? So this is something that I want to show you. This problem can be directly applied in the optimal drilling control, where you want to maximize the rate of penetration of the drill. And of course, the drill string is subject to axial and torsional effects, much like a flexible rod, right? So those force and velocity propagation can be modeled by a wave equation. So we have a cascade of this static map describing the maximization of the rate of penetration with a wave PDE. In that paper that I mentioned in the beginning of this part, we show how we can manage this problem using this theory. After that, we can go to the parabolic PDE case. We're going to start with the diffusion process and then the extension to a more involved class with advection and reaction terms as well. So in this point, I just replaced the wave PDE by this diffusion process. We have the same formulation again. Although we know the domain of the PDE or the diffusion coefficient, we don't know nothing about the map. We just know that this map has an extremum point. Again, the idea is to how to design the appropriate boundary control to this problem. We are using Dirichlet actuation, again, different from the previous section, previous part. This is the PDE for this case of the diffusion process. You can note that we are actuating there directly in the state of the boundary alpha dt, not in the special derivative of this. And in this publication in Automatica, we have shown the results for the gradient case. This is the Veiled block diagram, right? We have two solutions, one involving the infinite dimensional state and another one if we have we know this boundary signal in the input of the map. These controls are not so difficult to implement. They're relatively simple. Again, we need to redesign the additive jitter, right? And in this Newton case that we're going to show, we have to use the T-cut filter to try to estimate the inverse of the Hessian. I call your attention to the trajectory generation problem for the diffusion case. This is the resulting signal when we try to solve this problem. This signal is in this side of the PDE. Passing through the PDE, we can obtain a sine of omega t at this point. There's a chapter dedicated for trajectory generation problem in this blue book, right, by Professor Kristich. So I'm going to show some equations. Now you are more familiar with the equations. We are just replacing the transport PDE for this diffusion PDE. And if you compute the propagating the aerodynamics, we can obtain this expression. And we have this cascade of diffusion PDE with the ordinary differential system, which is simply an integrator again. and reminding you that here we have, again, the Dirichlet equation. So it's very difficult to prove the stability of this system. The idea is to apply the backtracking transformation and obtain a target system. It is not difficult to show that this PDE, once the boundaries are zero, that this PDE is finite time stable. And if it is finite time stable, this term is going to zero in finite time as well. And finally, since this dynamics input state is stable with respect to this input, we can conclude that var theta is going to zero as well. But var theta is just the propagate the error, right? And so we can achieve our control objective. So from this backstepping transformation, we can obtain this controller. I'll call your attention to this reference so that we can follow this expression. But this expression is not implementable because var theta has this term, and this term is unknown. This is the maximizer of the map. So what we will do, we will try to obtain an implementable version of this controller using average-based estimates. Basically, we need to remind that Z is gamma T, the Riccati filter, multiplied by the estimate of the gradient. This estimate of the gradient in average has this expression. If we put this in the previous equation, compute the average controller, we obtain this one. And replacing K bar by minus K, you obtain this expression. And locally, we can obtain a linearized version of Z, which is simple var theta. So we can replace var theta average by Z average. And the non-average version of the signal is simply the term between the brackets. So this signal is measurable, like that, and this controller is implementable. We can add the filter to apply the averaging theorem in finite dimensions, and of course, provide some inverse optimality results. We will not show this in this presentation, but we can follow other papers that we discuss about inverse optimality. This is the closed loop system. We can obtain exponential stability in H1 norm and the convergence of theta, capital theta, and y to the desired values. I call your attention in this theorem for the norm that we are using. We are now in the Sobolev space, and in the residual sets, we can see that they are different due to the additive jitter, which was computed using the trajectory generation problem. The sketch of the proof. We need to write the equations of the original system. After that, we compute the average closed loop system in this part. We apply the backstepping transformation to obtain the target system in average. After that, we prove the exponential stability of the target system using a Lyapunov-Krasovsky functional, like that. Here we have the exponential stability. After that, we can conclude that the average closed loop system is indeed stable, and we can obtain a practical stability of the original system, using this version of the averaging theorem in infinite dimensions proposed by Hayden Lunio in this reference. This is particularly important because the regular averaging theorem that we have used in Khalil's book is not applied for this kind of system. So we need to give particular attention to this part of the proof. Here we have some simulations. In this site, you can see that the system converges to the extremum according to these two figures. And the discussion that I'd like to mention here is that since the diffusion is a stable, open stable process, you can imagine it. Why not just applying the classical extremum seeking? Okay, if you do it, considering the same frequency that we have used here, you can see that the system goes unstable. The solution that we need to use to apply classical extremum seeking is to decrease the frequency. But if you decrease the frequency, this is the kind of the response that we will obtain. So you are sacrificing the convergence rate of the algorithm. So this is very interesting because it seems that it's a good idea to have a diffusion boundary control to compensate the PDE. Here we just compare both approaches, the gradient and the Newton, and indeed you can see that the Newton is faster than the gradient, as we talked before, even in the presence of the partial differential equations. Finally, I'm going to show the other case for the reaction diffusion process. We published these results in this International Journal of Adaptive Control and Signal Processing. These particular class of PDEs are important because you can use this, for example, to model biological reactors. And we have this type of equations, you can see that now we add a reaction term and an advection term in the previous diffusion system. For stability, we need to guarantee this relation, right? And we have a trajectory generation problem a little bit difficult, but this is the solution, right? And this is the final boundary control law for this case, for appropriate constants that we can see in the reference. Unfortunately, I cannot present this in this talk because of we don't have enough time for that. So we can prove stability and convergence using similar steps. And again, you need to pay attention to the final residual errors to do it to the inclusion of a different additive determinant. In particular, in this simulation, my intention was just to show that in the reaction, advection, diffusion process, we have different steady states. So in the input of the PD, in the output of the PD, they do not converge into the same values, right? But this is not a problem, it's just the nature of the problem. And in terms of application, you can see that reaction, advection, and diffusion process are being used, for example, to model distributed parameter tubular reactors. And basically, we can use this approach to find and maintain the optimal product rate. Okay, according having in mind that XS, the input, is the substrate concentration, and XP is the biomass concentration. This is very interesting, for example, to optimize the methane gas in fish industry. We have a publication on that, right? Finally, we show in this publication that in the multivariable scenario where we have to multiple inputs, denoted here in the case where we have two inputs, theta 1 and theta 2, we can have different PDEs in each channel. This is very important because it shows the potential of the approach. Basically, when you use this Vicat filter in the multivariable problem, the Newton algorithm effectively diagonalizes the map and allows the centralized compensator. So you can have different PDEs. In this case, we have diffusion PDEs with distinct diffusion coefficients, but you can have a delay equation here, or a transport PDE, a diffusion PDE, a wave PDE, and we can obtain a multivariable diffusion compensator for this kind of problem. And here we have a table summarizing all the algorithms that we have discussed until the moment. So I think this is a very interesting application of the first result involving delays, but we're going to consider a nonlinear PDE, right? This nonlinear PDE is like Wilfan and Richards are commonly used in the traffic congestion control problem. We published these results in this publication, and basically to control the flow dynamics, we can use hump metering and varying speed limit. Okay, these are the two forms of actuation. In this LWR model, we have a first order hyperbolic PDE, nonlinear, right? Because of this term. Rho is the traffic density, and V is the traffic speed. Of course, V is a function of Rho, as we show in this expression. Vf is the maximum velocity, and Rho m is the maximum density. We can obtain a fundamental diagram with an extremum point using this relation, right? So basically, in the downstream traffic bottleneck, we want to maximize the flow through the bottleneck using extremum seeking. So it's clear that the capacity drop at the bottleneck area, and this is very hard to model. Again, this is very appealing for extremum seeking. Basically, in the non-bottleneck area, we have this capacity, and in the bottleneck area, we have this one, right? We have a flow which is reduced. So we can write in the upstream traffic dynamics this equation, and in the bottleneck area, we can obtain this function. So the idea is to maximize the Q out under the presence of this nonlinear PDE. The interesting part is that we can obtain a linearized model for the LWR PDE, and this is simply transport equation. So we can just apply the predictor strategy that we discussed in the very beginning of the presentation. So we have a nonlinear PDE, but we can locally control it using predictor feedback. So in open loop, the outflow is decreasing. And when we apply the extremum seeking control, we can obtain maximized flow. This is the state evolution of the traffic density. And we can see that it converges to the optimal value whole store. The final result that we want to show was the extension to Nash equilibrium seeking in non-cooperative games on the delays. This work was co-authored by Professor Tam Bassar from University of Illinois at Bennett-Champaign. And this is a very interesting result because time delays are very common in these problems involving non-cooperative games. So we have the markets, player 1 and player 2 in a duopoly game. And the idea is to obtain the Nash equilibrium under delayed player actions. So this is a little bit different than extremum seeking because extremum seeking, we have multiple inputs and just one output. Here we have multiple inputs or player actions and multiple outputs that they are the payoff functions. The idea is the payoff function depends on the player actions of the other player, the player action of the other player. But in the non-cooperative scenario, we do not share information. So we need to design theta 1, theta 2 in this non-cooperative scenario. So this is the payoff functions. We can see clearly that they depend on the delayed player actions, both D1 and D2. And in this publication, in the Journal of Optimization Theory, we consider the general setup within players, but we restrict ourselves to the duopoly game here. And basically, we can see this is the definition of the Nash equilibrium, right? Once the player 2 achieves the Nash equilibrium, the only way the player 1 has to optimize his payoff function is to achieving the Nash equilibrium 2. In a similar way, you can interpret this other inequality. And the important part is that we can prove the existence of the Nash equilibrium according to this expression, but we need to guarantee the invertibility of this matrix. We call this matrix Haitian matrix, as in the previous problems. Note that we have an interaction between the players in this diagonal, and we can see that we have small parameters here, right? So this is the block diagram of the complete system. Here we have the game with the payoff functions, the delays, different delays for player 1 and player 2. And this is the predictor that we have introduced in the beginning of the presentation. In particular, we cannot estimate fully the matrix H, but you can estimate the diagonal terms. Player 1 can estimate this part of the matrix, and player 2 this part of the matrix. These terms cannot be estimated individually by each player. So since they are not sharing information, it's impossible to do this. But if you assume a small coupling parameter between the players, you can solve the problem using only the estimation of the main elements of the diagonal. So again, the proof uses the small gain theorem and infinite dimensions because of the delay. And in this sense, we can guarantee the Nash equilibrium effectiveness. You can see that when we do not compensate the delays, the system goes unstable using this classical approach proposed by Professor Kristich, his student, and Professor Bassar. And when we compensate the delays, as I talked before, we can see that we can achieve the Nash equilibrium. Even if the coupling parameter is large, it means that our solution, our demonstration, may be conservative, our assumption may be conservative, and there is a space to work a little bit more in this problem. So of course, we can consider more general partial differential equations rather than just transport PDE in the delay case. And in this paper in CDC, we consider heterogeneous games, non-cooperative games, using different PDEs in the inputs of the player, in the player action, sorry. And of course, we need to compensate the transport PDE for player 1 and the heat PDE for player 2. And here you can see that the system goes to the Nash equilibrium according to these 3D plots, right? So I would like to thank the collaborators, Professor Kristich, Professor Bassar, Professor Subakino, and other colleagues, Damir Hussiti, Jan Feeling, Shimon Kuga, Hu and Yu, Mamadou Diagni, and my PhD student, Victor Hugo Pereira, for all the help. So I'd like to thank the Brazilian funding agents, CAPES, CNPq, and FAPESG, and I will be pleased to answer some questions in the conference. Right? See you. Thank you. Bye-bye.